Hi everybody, welcome to this video on the basics of digital topography. So I'm really a geomorphologist. I study landscapes and I love digital topography. I love being able to render the landscape in different colors and shades and pick out different features that explain Earth history. So to me this is the most exciting thing and I want to share it with you. This is a picture of a shaded relief image of New England. This is Vermont, the Adirondacks, the White Mountains. There's so much to see here. I can't even get into it, but it is a motivator of why digital topography is so important and so useful. So in this video, I'm basically going to spend the first half introducing you to some of the commonly used elevation data sets, the NED, the SRTM, and then LIDAR data. And then once you know about those basics, then we'll look at how we can use that data to do some basic topographic analyses. We'll talk about hillshade images, slope, aspect, and finish with volume. So the first thing to know about digital topography is that digital topography data is stored in what's called a digital elevation model. And this is pretty straightforward. It's a grid of elevation values. Just like an image has a bunch of pixels with color values or brightness values, this is just a grid where each pixel is an elevation value in meters or feet above sea level. And we can either visualize this like an image that I just showed you, or we can use it for calculations like slope or aspect. Alright, so a major source of elevation data is the National Elevation Dataset, the NED. And this covers the entire US at a few different resolutions, everywhere from 30 meter down to 3.3 meter. And these are really compiled from different sources. A lot of the most basic 10 meter data is actually compiled from digitizing contour maps. And here's just a flavor of what kind of detail you might be able to see in some of those different resolutions. Here's the 30 meter pixels, here's the 10 meter pixels, and here's the 3 meter pixels. So you can imagine you can see a lot more detail in this high resolution 3 meter DEM. And you might use it therefore for different applications than the 30 meter. Another really important data set is the Shuttle Radar Topography Mission, or the SRTM. And this was amazing. Back, I think in 2001, this was collected. It was the first ever globally consistent elevation data set. Pretty much covered the whole globe using radar interferometry from a space shuttle. They put the space shuttle into orbit, they extended this huge boom antenna, and were actually able to do single pass interferometry and build an elevation data set for the whole world. And this is available in 3 different resolutions, 30 meter, 90 meter, or 1 kilometer pixels. And it has a vertical accuracy of at least 16 meters. In a lot of places it's much better than that. So basically this is a go-to data set if you're studying landscapes or any problems outside of the United States. Now the third category of digital topography I want to tell you about is LIDAR. Stands for light detection and ranging, and we've actually got a whole video about LIDAR if you want to check it out. So I'll just give you a preview here. Basically what happens is elevation data is collected by pulsing a laser from an airplane, measuring the time it takes that laser to go down and back. And because the laser shots are very small and can be shot out very quickly, we can collect a huge amount of data, often billions of shot points. And that lets us construct a digital elevation model that might be as fine as a 1/4 meter resolution. Okay, each pixel would be a 1/4 meter by a 1/4 meter. That lets us see amazing detail. Now, one caveat of LIDAR is that because it's flown by aircraft, not satellite, its spatial footprint is quite limited. You'll often find it just in tiles that are covering a town or a county. Some states are just now starting to get statewide LIDAR. So it's somewhat sparse. But here's an example of how powerful it can be. This is a 1.6 meter LIDAR DEM of the Middlebury River. Shows some amazing things. Here's a gravel pit. You can see these individual roads here. You can see this river canyon with some beautiful river terraces next to it. So amazing detail you can see in the LIDAR data. Where can you find it? A great place to look is the Open Topography website, which has a number of publicly available LIDAR data sets shown here. And then also a lot of state and local data distributors have LIDAR data. For example, VCGI in Vermont. Okay, so now you know something about these different flavors of elevation data sets, and if you're working in the United States, you'd probably be working with the NED or the LIDAR. If you're working internationally, you'd probably be working with the SRTM data. So let's look now at some things we can do with elevation data. And this is just a little bit of a preview of some of the simple things. We'll be getting into things like hydrologic analysis in a later video. So we'll start looking at hillshade, then we'll look at slope, aspect, and volume. All right, so what is a hillshade? We kind of take this for granted. Whenever you see digital topography, you're almost always looking at a hillshade or a shaded relief image, right? You're usually not looking at a grid of numbers because that's not very useful to our brains. What a hillshade is it lets us visualize the data. And the way it does that is that it shines an artificial light across the digital elevation. So in this case, the light is shining from an azimuth of 315 degrees, basically out of the northwest. And what you can see, the computer simulates places where there is a steep topography, or a lip in this case. It's basically the edge of a canyon or a precipice, are in the shadow, right? It recognizes that under these lighting conditions there would actually be a shadow cast here, and it creates a raster in which those pixels are assigned darker grayscale values. So each pixel in this hillshade is assigned a grayscale value, a digital number, from 0 to 255. In cases where it's in a shadow, that would be a low number, like 1 or 10, corresponding to a dark pixel. And then surfaces that are facing directly towards the sun, like this hill slope that's facing to the northwest, that is very bright because it's illuminated. So it would get a high digital number, like 250. So the important thing about a hillshade is that it's just another raster, it's another grid of numbers, but in this case, the numbers correspond to a theoretical illumination. They're high if it's brightly illuminated, they're low if it's in the shadows. And so a common way to display a hillshade is in conjunction with a digital elevation model. So in this example, we've actually got the hillshade sitting below a digital elevation model. The colors in this picture are coming from having assigned colors to different elevations in the DEM. And then we made that 60% transparent so you could see through those colors and actually pick up some of the shading in the underlying hillshade raster. Okay? So overlaying a DEM with a hillshade is common, making one of them transparent so you kind of get the best of both worlds, the shading and the elevation coloring. And of course, this is a great example. What do you see here? You don't have to be a geologist to see something here, right? Right away you see this line cutting through the topography. What could that possibly be? There's obviously a story to be told, and we wouldn't know that if we hadn't had this data. This is actually the Alpine Fault. It's a really important strike-slip fault running north to south in New Zealand. So here's a really important geologic feature that just pops right out of the DEM, and it's just an example of how powerful these can be. So I'll move on now to slope. Slope is important for a whole number of reasons, okay? In particular, slope of a hill, or of a slope of a slope, is really important in terms of landslide hazard. It's important in terms of implementing building codes. Many cities don't let you build on very steep slopes. In earth science, we might use slope to compute the mass balance of a glacier, or we might use slope to look at vulnerability to soil erosion. This is really just a partial list. You can think of dozens of examples of why slope is really important in all kinds of geospatial calculations. And this is just an example of how you might use this. Here's a digital elevation model it's a hillshade, overlain actually with a hazard map of shallow landslides. And what you can see here is that the shallow landslide hazard corresponds to the steeper slopes in this map. So it's just an example of how you could use a digital elevation model to compute slope hazard and then output a product that's really functional and useful. So how do we actually compute slope? Everybody knows that slope is rise over run, right? And we're used to thinking in 2 dimensions. So in this case, slope is simply the rise, or A, over the run, B. Okay? But in the real world, of course, we have 3 dimensions. We have maybe a north-south direction, an east-west direction, and then we have a vertical direction. So we have an X, a Y, and a Z. So computing the mean slope in 3 dimensions is a little bit trickier. And I'll show you 2 common approaches in this video. One is called the 4 nearest approach. And so in this approach, we're interested in computing the slope of this central pixel. Okay, so we're going to compute the slope of this middle pixel. And the way we're going to do it is we're going to consider what is the slope across it in the y direction and what is the slope across it in the x direction. And then we're basically going to use the Pythagorean theorem to combine those into a combined slope. So here's the slope in the x. It's rise over run. So keep in mind these are elevation values, right? 49, elevation of 49, elevation of 40. So the rise is given by 49 minus 40. That's right here, 49 minus 40 over the run. Now each of these pixels has a width of 10, okay? So the run across these 3 pixels is 20. It's basically 2 pixel widths. All right, so we got the rise over the run in the x dimension, and now we'll compute the rise over the run in the y dimension. That's 45 minus 48 divided by 20. And so now we have this slope in an x and a slope in the y, and we can estimate the combined slope using the Pythagorean theorem. And you might recall the Pythagorean theorem is a squared equals b squared plus c squared. And so we can rejigger that here to basically say the 3D slope is equal to the slope in the x direction squared, well, the square root of the slope in the x direction squared plus the slope in the y direction squared. So I'm skipping some steps here, but this is coming directly out of the Pythagorean theorem if you'd like to look that up. Now we're going to solve that. We'll plug in our x slope and our y slope squared. We'll take the square root, and we get a slope of 0.474 for this central pixel. Now that's a useful technique, but it could be argued that it's not very robust because it doesn't really incorporate all of the neighboring pixels. And of course, the true slope in this region is really defined by all 9 of these pixels, not just these 4 closest neighbors. So a slightly more robust approach is called the third order infinite approach. And in this case, what we do, we're going to determine the slope across all 3 of the cell pairs in the x and all 3 of the cell pairs in the y. So here we go. Here is the 3 cell pairs in the x. And what we're going to do, we're actually going to take the slope of this center one twice. We're going to acknowledge that because this is a bit these neighbors are kind of closer and more important, we're going to weight them by a factor of 2 more than the others. So the mathematics behind this are the rise is 47 minus 42 plus 2 times 49 minus 40 plus 52 minus 44 divided by the total run of all these, which is 4 times 20, or 80. And that gives us basically a mean, a kind of weighted mean slope in the x direction. And now we're going to do the same thing in the y direction. We're going to take a weighted mean slope in that y direction. And then we're going to again call in the Pythagorean theorem. A squared plus b squared equals c squared. And that'll give us the 3D slope equals this, and we'll solve that out. And in this case, we get a slightly different slope value, 0.42 instead of 0.47. So the main take-home point here is that there's 2 different ways to compute slope, and in many spatial computations, there's multiple ways to calculate a single parameter. So it's always important to understand which approach you're using and exactly how it works. So we'll start winding down here. Another really important thing you can compute from digital elevation models is the aspect. Okay? The aspect can be thought of as the compass direction, or the azimuth direction, of the steepest gradient, also known as which way is a slope facing. Okay? So if this is a map of azimuth. So in this case, this blue slope right here is facing basically west and southwest, okay? And this yellow slope is basically facing east and northeast. So from that, you can infer that this is a river valley, and this is one hill slope on one side, this is a hill slope on the other side, facing in opposite directions, okay? This over here is a volcano. And of course, this has all the aspects. Here we've got our westerly aspects, our northerly, easterly, and southerly aspects. So why does aspect matter? Well, if you're a botanist or biologist, you know why. It controls how much sunlight you get and when you get it. Southern aspects tend to get a lot more sunlight. Northern aspects get a lot less. So this has a direct control on the type of vegetation that grows on hill slopes, and is a really important parameter in things like vegetation modeling, fire modeling. It's also really important in terms of avalanche danger. Solar heating of snow-packed hill slopes governs avalanche danger, and so aspect is one of the huge variables in predicting avalanche danger. And so we'll finish by just pointing out that digital elevation models are fantastic for computing volumes, okay? And a great example of that is how much material was erupted during the Mount St. Helens eruption. So here we've got a digital elevation model from before the eruption, and then here's the same digital elevation model from after the eruption. So simply by subtracting the surface after from the surface before, that's going to give you the vertical difference for each pixel, and then multiplying that by the area of each pixel would actually give you the differential volume between these two scenarios. So digital elevation models can be a great way to estimate volumes of lakes or other natural objects in the world. So thanks for listening. We looked at commonly used elevation data sets, and then we went through some basic topographic metrics that you can compute from a DEM. Take care.